Welcome to the Qlik Best Practices breakout session for the 2016 Virtual User Group. The focus of this session will be performance and optimization. The majority of the best practices covered today will apply to both Qlik View and Qlik Sense applications, making this a valuable deep dive for Qlik developers everywhere, whether they are developing in Qlik View or Qlik Sense, or even in printing that leverages the Qlik engine to produce reports. The purpose is to help you write Qlik applications that will maintain their cutting-edge performance and optimization, even as data volumes and complexity steadily increases. Having a deep understanding of performance and optimization will help ensure that the applications that you write in Qlik can scale to meet the growing demands of your organization. My name is Johnny Poole, and I'll be your presenter for the next 60 minutes. I've been with Qlik for 5 years, and I am currently a Principal Solution Architect in Qlik's pre-sales organization. You can find me publicly as an active member of a vibrant Qlik community at the link on the screen, where I do my best to guide and assist other Qlik practitioners while continuously learning from the Qlik luminaries from around the world. If you haven't already, I would urge you to join Qlik community so that you can access all the resources and blogs from the Qlik luminaries from around the world as well. Today's agenda is ambitious and will be divided into 5 sections. The first and most important session today is a deep dive into Qlik's core technology and understand how it organizes and stores data. Understanding Qlik's unique storage model is key to understanding its compression algorithm and how Qlik scales and why a best practice is in fact a best practice. It will tell us what to expect when data volumes grow and how to relieve the potential performance bottlenecks. Having this foreknowledge will save you development time and help ensure that the applications that you write will withstand greater user demands without significant maintenance. I hope you will find this section insightful, as I did when I first discovered these materials. A number of best practices will be covered, from data modeling, expression syntax, and data loading. We can't cover every best practice, but for the best practices that we do cover, I will relate back to Qlik's storage model to help you understand why the best practice is a best practice. We will wrap up this section with a synopsis of how to bring everything we've learned in order to make the best guess trade-offs between maintenance and performance. While the theory is accurate and most best practices have been proven in the lab with benchmarking, not everything is perfect, and the art and science of writing the best Qlik application for a specific business need is ongoing. Next, we'll have a look at how modern CPUs respond to Qlik's in-memory data and what to look out for as larger and larger sets of data are deployed to users via Qlik applications. There are a number of best practices here that will ensure that your Qlik environment is properly set up to maximize your investment in Qlik and ensure that Qlik's amazing engine is running without latency on your platform. Sections 3 through 5, we get into advanced development approaches to progressively scale our Qlik applications. Data segmentation, a common approach in Qlik View, will be increasingly possible in Qlik Sense, and you will get an idea of when to leverage Qlik's hybrid approach, direct discovery. Finally, on-demand app generation brings a very modern, almost cloud-like approach to data analytics by delivering an elastic or on-demand approach to spinning up user-requested data sets for exploration. Let's get started. Qlik's core technology involves loading compressed data into memory. This enables agile and interactive search and visual exploration of a fully indexed and optimized data set that itself comes from one or more tables, systems, or data sources. Because the compression algorithm accelerates as data volumes increase, the approach has been reliably used to load up hundreds of millions to billions of rows of data on a per-application basis. I just mentioned that Qlik's compression algorithm accelerates as data volumes increase. What does that mean? Well, when Qlik loads data from databases, data systems, and other sources, it keeps track of every single unique data value. In fact, for each data field, Qlik will store the text value of each unique value just once. It will store one copy of each of your full product names, your customer names, your dates, your revenue amounts, etc. And this is the case for all data types. If you loaded it into Qlik, Qlik applies this storage methodology. Then, as Qlik gradually comes to understand the full variety of possible data values within each field, it can achieve some economies of scale even as you may continue to load more and more rows of data. The effect is that the greater the number of rows added into the individual application, the less computer memory, or RAM, is required to handle those increases. As you can see on screen, the curve this results in is a very attractive scalability curve that allows organizations to reliably predict and deploy Qlik and progressively add more users, more applications, and more data. Let's take an even deeper look. As Qlik loads rows of data, it translates and stores the data in two ways. The first is that it creates a two-column key pair table called a symbol table for each field. Qlik does this for every field that you load into a Qlik application, so that if you load 100 fields, your application will include 100 symbol tables. Each row of the symbol table contains a unique data value that was encountered when Qlik loaded data from a source. The second column of the key pair is a pointer value, or a shorthand reference to the full data value. In technical terms, the pointer is called a bit-stuffed pointer. A bit-stuffed pointer value is reflected on screen as a string of ones or zeros. What is neat about a bit-stuffed pointer is that the amount of storage space an individual value needs depends on the length of the actual pointer value. So the first bit-stuffed pointers that appear in a symbol table represent relatively light storage, and the later ones, particularly as we get into millions of unique values within a certain field, represent proportionally larger values. These bit-stuffed pointer values are also referenced in the data tables. The data tables are the second way that Qlik stores data. For each table of data that is in your actual application, Qlik creates a data table that replaces all the real data values with a bit-stuffed pointer value equivalence. The storage model on screen is instrumental in understanding Qlik's ability to scale and why best practices are best practices. Because I will refer to this screen multiple times in the subsequent slides, I suggest taking a screenshot of the screen so that you can refer back to it as needed. In the next slide, we will apply the pure science of the storage model to the effect of actually loading data. In the colored grid on screen, I want to draw your attention to the field names that represent the columns of a fictional set of data fields. You can see that this application loads 5 years of information and has a date field, which stores a unique day value for every day in the past 5 years. 5 years times 365 days equals 1,825 unique day values. So, when Qlik needs to load 5 years of information, it will often do so by loading a maximum of just 1,825 rows of unique day data values stored in a symbol table. Qlik will do this for all the loaded fields, including, hypothetically, your organization's 10,000 products for the past 5 years, the 50,000 customers, and the 10 million unique sales transactions. If this were a sales application, all of this data would be loaded and indexed. Looking at the left side axis of the grid, you will notice that as more records are loaded, the symbol tables for each of these fields max out. Quite simply, as all the possible customers, products, and other information is loaded from the source, Qlik becomes saturated as it learns the full variety of possible data values. In the first few records, each record will result in new rows in most, if not all, the symbol tables. This phase is represented in red and represents a relatively steep demand for more RAM as more and more unique data values are loaded into Qlik. But as each symbol table maxes out, Qlik reaches inflection points in the scalability curve, and the declining need to grow the symbol tables as well as some of the data tables results in ever-declining need for more RAM. Eventually, just a few symbol tables, probably from the main fact table, will continue to grow in size, resulting in the final phase of minimal growth, represented in green in the bottom right corner. For those of you who are working with both platforms, the storage model and the accelerating compression model that you see on screen is applicable to both QlikView and QlikSense applications. The difference with QlikSense is that the data retrieval or access against the storage model is done using a columnar method. A great document that helps explains the true power of Qlik's accelerating compression algorithm can be seen in the recent QlikSense data scalability white paper. Taken from this white paper, you can see one example on screen of how an existing application that has loaded 100 million rows of data requires 20.6 gigabytes of RAM on the Qlik server. Then, when 50% more additional data is loaded, up to 150 million records, Qlik needs just a 3.9% increase in RAM to approximately 21.4 gigabytes of RAM. As well, when loading 100% more additional data to 200 million rows, this just requires a 5.8 increase in the RAM. The difference reflects a tapering need to read in more data and use more storage. Let's reflect on this for a second. Qlik's ability to load and integrate multiple sets of related data, potentially from many different sources, and optimize that set of data for search and visual exploration is a game-changing capability. But a key foundation to realizing this is Qlik's reliable approach to scalability, which itself is a result of the Qlik storage model that produces an accelerating degree of data compression. Now let's apply this theory to some of the best practices. Let's start with the data model. The following best practices have long been known to help scale Qlik applications. A few examples are removing synthetic keys from the data model, removing system keys and timestamps from the data model, unused fields removed from the data model, and removing unneeded snowflake tables. In other words, consolidating your data tables. Another way is to break concatenated dimensional fields into distinct component fields. Removing the linked tables from very large data models and table concatenation is also a possible alternative. Using integers to join tables where possible, as well as using the auto-number function to replace large concatenated keys. Let's take a look at some of these and how they relate to Qlik's storage model. Here are three examples. Dropping unused fields is made easy by leveraging Rob Wunderlich's Document Analyzer app that you can find in his QlikView cookbook. The analyzer figures out which data fields that you loaded into your application that are not actually leveraged in the logic or the presentation layer. These unnecessary fields can be instantly recognized and discarded, ensuring that you are only loading and indexing the pieces of data necessary for the consumption. The effect of removing a whole data field means purging an entire symbol table, as well as removing one column from the associated data table. This will be disproportionately effective if that symbol table contains millions or a large number of unique value. It will be much less effective if that field in question is just a flag storing perhaps just two values. So put an emphasis on assessing and hopefully discarding fields that are highly unique. Along the same lines, it is helpful to trim unnecessary detail from an individual field. Take a date field that stores both the day value as well as the hour and the minute. In a single field, if we keep track of just the unique days, that's 1,825 values over 5 years. However, if we store down to the hour and minute, that's 157 million possible unique minutes over 5 years. That's a huge symbol table that is begging to be removed or at least assessed. If you do need the detail, there may still be hope. Simply split the date and time portions into two fields. You will only have 1,825 symbol values for the date component and just 24 hours times 60 minutes, or 1,440 unique possible minute values. Two symbol tables, each with 1,000 to 2,000 values, will be far more efficient than one giant symbol table with 157 million records. The lesson is to think about not only the kind of detail your user needs to consume, but how it's best to store that detail in Qlik. There is another helpful tool out there. and that is the AutoNumber function that will replace actual data values that are highly unique with efficient integer values. Qlik will still create a symbol table for those new integer values, but the values usually require less space than the original data values. This is very common with concatenated keys. It's helpful when working with fields with lots of unique values that, while needed for the logic of the application, do not need to be displayed on screen to the user. The key lesson here is to be aware of your most unique fields, and if the uniqueness is needed for display or logic purposes, think about the most efficient way to store that detail for the best possible performance and optimization. As shown earlier, there are a number of other best practices, including consolidating data tables, but the uniqueness topics discussed here are a major area for optimization gains. Let's pivot and have a look at some best practices for expressions. Qlik's engine calculates UI expressions on the fly, and they are often recalculated with every user click as the users explore the data. Let's take a look at how we can make expressions more efficient. One example are nested if statements. A common way to write conditional expressions is to leverage the nested if statement, probably because a nested if is a common method applicable to many software packages. But there are alternatives, and in Qlik, in the top right, we can use a match function with the pick function to bucket a delimited list of data values alongside a corresponding delimited list of replacement values. At volume, this expression can be more efficient. And if the expression itself seems a little dense or unmanageable, we can provide a mapping table in the data load that would auto-replace a region value with a replacement data value that can directly be used in the UI without a need to work out and recalculate those conditions every time a user clicks the mouse. This is more efficient. Let's take a look at some other examples. On screen, you will see another example of a nested condition. This time, the if statement is applied within an aggregation function. In this example, we can improve things slightly by getting rid of the string comparison by comparing against an equivalent integer replacement value that is calculated in the data load. This is called minimizing string comparisons. On screen, you can see an even better option by removing both the string comparison as well as the if statement by replacing it with set analysis. The new numeric field can be determined via a data join in the model or by using the mapping load technique mentioned in the earlier slide. Perhaps one of the best expression optimization techniques I can repeat here is the use of Boolean flags to streamline both the data model and the expression calculation. At the top, you can see a syntactically correct way of using set analysis to aggregate sales numbers for just the current year to date. Now, if we calculate a yes, no, or 1 or 0 data value flag in the data model that determines whether each date is within the current year to date, we can streamline the set analysis by doing a simple integer comparison within the set analysis to achieve a potentially faster expression. Taking it a step further, we can even do away entirely with the comparison by replacing the set analysis with a very simple arithmetic expression that will still aggregate to the same result, but often perform better. Boolean flags eliminate unnecessary if statements and other conditional expressions. Sometimes you can get rid of set analysis. Boolean flags are a tool of choice because by adding a symbol table with just 2 unique values to represent the 2 Boolean options, this represents a very light footprint in the data model and makes the performance in the UI much faster, and it's often well worth it. A common conundrum in business intelligence as a whole is presenting users with access to wide and detailed tabular data sets. Creating a spreadsheet like front-end in Qlik is an inefficient use of the technology and is a relatively slow operation, particularly when we are talking about dozens, if not hundreds of fields. What is recommended is to introduce UI design controls that prevent the automatic display of all the fields and rather have the user select the fields that they are interested in. From a developer standpoint, what is important with this technique is that you use not only the conditional show-hide features on the fields in the table object, but that you add a calculation condition for the entire object as a whole. Without the calculation condition, the Qlik server will still calculate the full tabular data set, even if the user isn't rendering all the fields in the browser. Optionally, you can limit the total number of dimensions, measures, and other fields that a user can select, ensuring that these conditions also reference in the calculation condition of the chart. Finally, address with the business users whether they actually need to see the detailed data in Qlik, or whether they are just trying to view all the data together so that they can download it to Excel. If they aren't doing detailed analysis of the raw tabular data in Qlik, consider using end-printing on-demand buttons in the Qlik interfaces that would allow the user to push and pass their filtered detailed data requests to the end-printing engine to produce a detailed formatted spreadsheet through a different reporting queue. This would avoid the inevitable user issues associated with the user having to watch and wait an hourglass as Qlik attempts to provide a massive tabular data set through the visual user interface. A couple of other points worth mentioning are as follows. If possible, avoid aggr. Aggr, which is a Qlik function to apply 2 or more passes of aggregation to the raw data records, is an expensive function, especially as data volumes increase. I don't have too many alternatives to offer here, but consider pre-aggregating some of the data in the data model so that you don't need to do the second pass, thereby getting rid of the aggr function. The number of records in a pre-aggregated data table that is added to the data model may be relatively low and worth adding in exchange for faster user interface. Data segmentation in Section 3 may also provide a way of pushing less data through the aggr function as the user explores a relatively small segment or partition of the data set in an array of Qlik applications rather than a single monolithic Qlik application. Now, aggr is often used in chart dimensions, and calculated chart dimensions are slow as well. If possible, avoid doing a chart dimension calculation and do it in the data model script. If you're using aggr in the chart dimension, you will be alleviating 2 possible bottlenecks in the calculation of that chart object. Also, there is some evidence in the benchmarking that using fields from 3 to 4 or even more tables in the data model to produce a single chart or a single table in the UI can be slow. The number of data hops, as we call them, that the engine must make can influence performance in these scenarios, particularly if there is a large intermediary data table in the middle of these hops. Consider leveraging the techniques mentioned in the previous slide to streamline viewing wide tabular data sets. In addition, and if possible, you may need to look at joining or concatenating the data tables in your data model to produce a model with fewer tables and fewer hops. This may not be ideal from a maintenance and overall readability of your Qlik application design, especially when viewed by another person, but it's a trade-off that could resolve in resolving your performance bottleneck. When it comes to data loading, there are several approaches to load small or larger amounts of data quickly, and most leverage the reusable QVD layer that is available to both QlikSense and QlikView. QVDs represent an intermediary step in the data load and data transformation. In addition to minimizing data flows and maximizing the reuse of business logic, the use of QVDs help us develop the right data loading strategy for different situations and can be used to scale a variety of data loading scenarios. Now, loading in Qlik is a serial process done by a sequence of steps in a load script. When the ability to integrate data from a variety of tables, areas, systems, and sources is so accessible, it's common to introduce the necessary business logic and transformation that will integrate and index the newly combined data set for the end users. That's what Qlik does. Now, adding multiple transformations on larger data sets can slow down the data load and push us towards solutions that will alleviate bottlenecks in the data load. The whole purpose is to provide rich, deep data sets for the user consumption through Qlik's award-winning, highly performant engine. The three main topics that will be briefly discussed here are optimized QVD loads, incremental loading, and parallel loading. When loading data from a QVD, expect the load to be fast. Qlik can load hundreds of thousands of records per second from a QVD, making it easy to load a large historical set of data or a vast array of transactional data very quickly. This is only possible, however, when the QVD load is what we call optimized. Broadly speaking, QVD loads are no longer optimized when significant transformations are done during the load of the QVD. To set up QVDs for rapid reloading, it's imperative that most, if not all, the transformations be done in advance of the QVD creation, perhaps in the raw SQL being sent to the source system or during a multi-threaded parallel load in Qlik's engine. Incremental loading allows us to leverage the optimization of an optimized QVD load to load historical data that has already been into Qlik and combine it with a new or delta set of data brought back from the source system. Even with millions of rows of data in a Qlik application, it is possible to deploy rapidly refreshing applications that push the raw data updates to the users in just one or a few minutes, without sacrificing the optimized nature of the in-memory data set that Qlik provides to the users. QlikView users will be happy to learn that the new WebSockets-enabled web architecture of QlikSense allows rapidly refreshing applications without interrupting users with active sessions. Finally, parallel loading is the technique of taking one long serial script over all of the data and sending just a segment of the data through n copies of the script. Each copy of the script has a different filter responsible for one segment of the data. With this technique, n processes will work in parallel to produce n segmented QVDs, which, in a follow-up script or follow-up step, can be rapidly re-amalgamated together to produce a single optimized data set. Parallel loading offers some options to load a vast amount of new data as quickly as possible. Whether you are working with high volumes of new data or just a very tight bottleneck in pulling data over the cloud, these three techniques will help you load data as quickly and as efficiently as possible. To summarize, leverage QVDs, not just for the techniques they open up for data loading, but also for its governance qualities of promoting the reuse of data loads across applications while centralizing the business transformations in one place. To ensure you're using optimized QVD loads, where possible, push sophisticated logic into the SQL layer. And remember, each technique is not a one-size-fits-all. Different techniques resolve different bottlenecks. Not discussed here at length is a relatively new way of bypassing QVDs called dynamic data update, which streamlines the movement of relatively low amounts of data directly into a Qlik application without a QVD layer. This is possible in QlikView, and there are techniques to leverage it in QlikSense as well to deliver near real-time applications in Qlik while still leveraging Qlik's optimized data layer. A quick note on governance and manageability. It's worth noting that creating a centralized data dictionary in any Qlik accessible data source is a great way to centralize business logic across multiple applications and quickly adjust that logic without needing to publish new code. On screen is a tabular view of such a data dictionary, where each row represents a variabilized expression that is syntactically accurate in the Qlik application it's targeted for. In practice, Qlik can loop through the rows of variables in this tabular data set dynamically in the load script, creating all the variables that the existing application needs while loading the data. If an expression needs to be updated, simply update the dictionary, and upon the next automated reload, the Qlik application will dynamically be updated with no need to republish the app and with no administrative intervention. Finally, to complete section 1, let's talk about the trade-offs to optimization and what we've learned. Starting in the top right, you should be minimizing nested if statements and other expensive functions, and even some set analysis, by resolving those calculations in the data model. You won't do this for all, but you will do it for some. Leveraging mapping loads, Boolean flags, and aggregate tables will allow you to maintain a lean data model with the right trade-off. Also consider creating variables for your expressions and a data dictionary for ease of governance and maintenance. On the left-hand side, consider lightening the data model by removing uniqueness and replacing it with more efficient storage options. Do this by removing an entire field or by changing the way you store a specific field, perhaps splitting it across multiple fields or aggregating it to store less detail. Remember the symbol and data tables and the size of each of those in order to give some guidance on whether your next data model change could have significant impact on the storage and optimization of your Qlik application. Any of these transformations can also be variabilized for efficient management of the data load, so move your transformations into the data dictionary and they can be used there as well. Where possible, use QVDs to reduce the necessary data flows and avoid reloading the same data multiple times across applications or within an application. What have we learned? In Section 1, we learned that the scalability curve in Qlik is very attractive, and it seems like we can load millions and millions of lines of data with great compression. This works especially if we follow the best practices. We can push this model as far as it can go. So what else should I look out for as we scale up the data volumes? In the following section, we will discuss hardware bottlenecks. Section 2, Data in Motion. As we load data into Qlik, and if we mind how to handle uniqueness well, RAM itself is rarely a bottleneck for Qlik. However, all that data moving around in RAM must be worked on, and it turns out Qlik is sensitive to certain hardware configurations that can either throttle or constrict the amount of data flowing between the RAM and the CPUs. Inefficient CPU configurations will generally be a performance bottleneck before RAM is, and it's important to discuss what those are so that you set up a good platform for Qlik's optimized engine. A key metric is the number of QPIs that exist in the CPU architecture. A QPI is a point-to-point connection between the CPUs on a server. And quite simply, the fewer KP hops there are in a multiprocessor configuration, the fewer opportunities for bottlenecks to occur as more RAM and CPUs are deployed on a Qlik server. In the following diagram, you will see a two-core configuration in dark green. The hash green squares on the sides of the cores represent RAM slots. To get data in RAM from one slot to either of the two cores, to crunch the numbers for the users of a Qlik application, the data must travel through the memory bus and potentially through a QPI to the other core. So lesson number 1 is maximize the memory bus speed, and that's important in your CPU selection, even if it means sacrificing some RAM. Lesson number 2 is seen when we add 2 more cores. Some configurations do not offer a diagonal QPI to connect all the processors in one hop. So with this configuration, the processor may be sending RAM across 2 different QPI hops to reach the core that will ultimately be doing the work as dictated by the operating system. Multiple QPI hops is not efficient, and it's important to minimize the maximum number of hops in your hardware selections. As you can see in the final configuration, those kinds of hardware sets are available. Once you know the RAM and CPU needed to deploy your Qlik application, ensure that you pick chipsets that are following the best practices and have minimal QPI hops. We call these hardware whitelisted hardware. While choosing whitelisted hardware, even if you are dealing with a virtual environment, consider the following additional best practices. Select the whitelisted hardware. Avoid AMD. With whitelisted servers, where possible, select the options with the faster clock speeds. Install memory according to the manufacturer's specs. And avoid installing more memory if that means that the bus speed will drop. In addition to these are the following recommended server settings applied at the BIOS and operating system levels. You can find a link on screen at Qlik Community. On screen, you will see a sample of whitelisted hardware that has been benchmarked with Qlik to perform well. Not all the possible whitelisted hardware is actually listed here. We just don't have time to test every piece of hardware out there. However, consult your local sales organization to cross-check if the hardware you would like to deploy on is good for Qlik. Common cloud solutions like Amazon do benchmark well with Qlik as well. And likewise, please check with Qlik on the cloud provider that you intend to work with. When it comes to virtualization, please follow all the best practices for the underlying hardware that we have already discussed. And then ensure that you dedicate the resources to the VM instance running Qlik. A list of other best practices are noted on screen. Please feel free to request a copy of Qlik's full virtualization best practices from your local sales team to ensure that your virtualization environment is tuned for both virtualization and the physical hardware underneath that virtualization. So far, we have mostly been talking about how Qlik scales on a per application basis. In Section 3, we will talk about data segmentation and how we can reset that whole performance curve. It is possible to get even more scalability if we split one large monolithic application into an array of related applications. What makes this possible is Qlik's ability to pass context and filters from one application to another related application, allowing the user to move between applications and not lose their data context. I've heard this being called drill-through Qlik style, but its real technical name, at least in QlikView, is called document chaining. You'll be happy to hear that this ability to pass parameters from one application to another is also being made available in the upcoming Qlik Sense 2.2 release. Yay! In addition, QlikView also has the ability to auto-segment applications by unique field identifier. This segregates a large single detailed document into n number of documents. This feature is called loop and reduce. Very large applications represent a disproportionate amount of data because the data is being highly compressed thanks to Qlik's accelerating data compression algorithm. What this means is that large application sizes means huge data volumes, and even with optimal hardware, smaller applications have faster performance. So why not split the one application into many? Loop and reduce will split a large, usually detail application over a key value like month. As long as that key data value is in the data model, the publish component will automatically produce a different document with just that 1 month's data set for each month. If a user wants to see a different month, a new identical application is loaded into the browser. Each time the user wants to do analysis, he or she does so using a document with a relatively low or optimal set of data. This allows Qlik to spread its amazing data optimization capabilities over multiple applications and achieve a new level of data scalability. The glue between all of these applications is document chaining, where every time the user wants to change their key data context, like month, the user's current filters are passed to bring up a new document via a parameterized URL. In the back end, a single year's worth monolithic application of the single year's worth of data can be divided into 12 smaller individual applications, all URL accessible through a parameterized URL. What does this mean? Well, you can reset the scalability curve and push out CPU and other bottlenecking by a factor of n, where n is the number of partition detailed applications produced by loop and reduce or other segmentation techniques. N is not an infinite number, and it's easiest to manage this kind of deployment if the number is relatively low. The one caveat with using data segmentation, which collectively includes both loop and reduce and document chaining, is that the business audience must find a natural breakpoint at which to divide the analytics when they're analyzing data at the segmented or detailed level. For example, if they need to see 2 months of detailed data together or do some aggregation just on those 2 months, month may not be the right field to segment upon. You can always have a summary and a detail application with 2 different user interfaces work together with document chaining, but you will still need to work with a business to identify a breakpoint when the data is analyzed at the detail level, because they can't analyze everything at once using segmentation. The good news is that it can be any field in the data model, and if you don't have one right now in your current data model, it may be easier to add a new derived field and send that new derived field to publisher to create that necessary segmentation. Everything we have so far talked about refers to in-memory applications. And on the screen, we can get a feel for the development effort versus the data volume that single or multiple segmented Qlik applications can deliver when in memory. Greater data volumes can be deployed using Qlik segmentation. They require a bit more maintenance, and there is that business caveat that the business can accept some measure of segmentation in their analysis of the detailed data. As a synopsis, leverage best practices and deploy on whitelisted hardware. Do leverage the in-memory techniques because it means all of your data is indexed and optimized, providing industry-leading performance in complex data scenarios with 1 or more related areas. But choose the appropriate technique depending on what you can achieve. Direct discovery. In Section 4, we will discuss direct discovery. Direct discovery is a hybrid in-memory on-disk solution that QlikView and both QlikSense support. You don't have to preload all the data. Direct discovery can make a larger amount of data available to the user, and it can help with some near real-time scenarios. With this approach, Qlik auto-generates the SQL that is sent to the database every time a user makes a click in the application, perhaps a data filter, perhaps a drill. This is pretty much the model with most of the competing technologies in the market who use basically direct discovery and not optimized in-memory data as their principal query method. In Qlik, the technique is applied in specific scenarios only. Sending live SQL to the source system creates a performance situation typically unknown to Qlik practitioners. The experience of the user is largely dependent on the structure and optimization of a different data storage system like a database or a data lake. Direct discovery has a few caveats, but a big one is that you'll be restricted on the Qlik expressions and Qlik functions that you can use against the direct discovery data source, as not everything that Qlik can do can be translated into SQL. So direct discovery is not usually a solution for more complex analytics, but it can serve and help us out for some simple scenarios. The 2 main ways of using direct discovery that I usually think about is number 1, simply build a single Qlik application that leverages direct discovery, giving you near real-time access to your detailed data. Or you can use direct discovery in conjunction with document chaining instead of using loop and reduce. Remember, loop and reduce is typically used to segment the detailed portion of your data. But with direct discovery, we don't need to load and resegment the data using loop and reduce. Rather, we can use a single detailed application that provides direct access to the data. Simply leave it as source and allow direct discovery to provide basically a data viewing capabilities on the detailed data. For the summarized data, you can still use the advanced in-memory approaches and syntax and do advanced analytics. Now let's add both of those options onto our growing diagram of solutions. In the top left, we have a new class of deploying simple analytics over large data sets using Qlik Direct Discovery with a single application. In the top right, doing advanced analytics on a summary application, we can segment the detail using Direct Discovery to provide detailed data viewing capabilities over those detailed records. Not for sophisticated analysis, but again, for simple data viewing. What else is there? There is one final approach that we will discuss in this session, and that is on-demand app generation. On-demand app generation is very modern and very slick. With this approach, the Qlik analytics become elastic. Instead of deploying set applications that are always deployed and always reloaded and always available for consumptions, users are given a selection page of data filters and data field selectors to pick the subset of data that they wish to analyze. Then, at the click of a button, Qlik requests and loads that set of data from the source into a pre-built application template, which is then provided to the user who requested it for consumption. The pre-built application may be all the user wants, displaying some summarized numbers and detailed facts for the data that they requested. Or, in Qlik Sense, the user can drag and drop and customize or completely change the user interface that has been provided to them, all the while using just the data that they requested. All of this is done using optimized, indexed in-memory data sets. But this time, the user requested the data that the user requested is persisted for a time period after which it is thrown away. It's a rapid spin-up, spin-down approach that has made many huge technology platforms wildly successful like VMware, Amazon, and others. So what do you get with on-demand app generation? The user has access to load the data they want from data systems that may have billions of records. By loading the data is indexed and optimized, giving them the full breadth of analytics and visualization that Qlik has to offer. The performance is great, and we know best practices are followed because the initial Qlik template and application is pre-built, and it uses approved data modeling techniques and UI design. More information about on-demand app generation is available on Qlik Community. Just search for on-demand app generation. Getting back to our solution set, now in the top right, we've come up with an approach where we can apply the Qlik engine to many users over a data set that runs well into the billions of rows of data. It's an option for Qlik View, and it's an option for Qlik Sense. Check it out. A simplified decision tree helps figure out which approach to use, but remember, always use best practices and always use good hardware selection. It will ensure that the data storage model that you learned about way back in Section 1 will bring the biggest business value.